Hey guys, let's look into the mass transfer basics. So guys, today we have mass transfer with us and we are going to consider pure basics. And here, first of all, we will just know what is mass transfer actually. So as you can see in the name itself, there is mass and there is its transfer. So why is it? Why the transfer is possible? Why mass needs to transfer? So and how it transfers? So let us just consider that there are these particles and there is an empty space, okay, or let's say there is a space with different particle or fluid. So this particle moves into the fluid and this is diffusion. So why does it happen? Here the particle have a high concentration and here low concentration. Okay, so let's see an example first. Let's consider that this is a mixture of A and B. Okay, so these two particles are of A and this is of B. So now let us consider that this is an empty space and it is filled with fluid. What happens that you will generally notice that a particle will try to obtain some space around it. So it will just try to move and get away from this crowd. So if we consider that these are a group of persons, then everyone wants to just have a certain space. And with this particle will actually go to a place where the concentration, okay, so let's talk about that. There is no A. So here is no A, no B. That's why from higher concentration, A will move on to the lower concentration and B will move on to lower concentration and A. So this is like from a point they are moving away. So they are diffusing into this fluid that's around them. Earlier we just put, so like if we just put a drop of ink, like here we have this dropper and there's a drop of ink in the water. So it will move to the water phase and will generally slowly and gradually with time the whole water will be with the color of the ink. That is diffusion, that is molecular diffusion. So now where particle A is smaller than B, we can see, so particle A actually can move faster and be a little slower. So the diffusion of both particle A and B may vary. So how can it vary? Remember, we are considering mass. So the mass could be different. But how to analyze it? How to quantify it? So to quantify it, we will take a term called mass concentration. Let's denote it with mu. So this is rho. Let's denote it with rho and let the mass concentration of a species in the mixture or solution be rho I. So what is this? This is actually mass of ith species upon the volume of solution. Okay. Similar way, we can take mole concentration or molar concentration. Molar concentration. And this we could denote it by Ci of species I. Okay. So these are two ways we can actually analyze or quantify the mass movement. Okay. But there we said that particle A, B will have a certain different velocity and particle A will have a certain different velocity. So what really we mean is that different particle can have different velocities. Okay. So let us consider that particle A has a velocity UA and particle B has a velocity UB. So how to average the velocity? Because we cannot see in the solution the diffusion is happening with this much velocity. So how to quantify it? So we can take a statistical mean. So let's take u, small u. Okay. So let's take this bar. They are moving with this average. Particle A is moving with average velocity of all the particles A and particle B is moving with average velocity of all the particles B. So let's take u. This is actually nothing but sum up. What particles do we have? So we have to take mass concentration and the velocity of this mass concentration divided by the total mass concentration. So in a way, what is this? This is mass velocity. Mass velocity. And this is average mass velocity. So what we are doing, the different particle with rho I with different ui, taking the sum, and we know that summation rho I is nothing but rho, because adding all the mass upon volume, so it will be the total density. Next we move on to molar average molar velocity. Quite similar to mass velocity, it is capital U, let's denote it with capital U, and it is summation of mass. So it's molar concentration. So we have to take molar and velocity upon summation of Ci, which is again summation of Ci, different concentration of with different velocity. And so we can take it like these are bars, so we can take them different mean velocities and upon C. C is the total concentration. So what is happening actually? From high concentration to low concentration, particles are moving, but they are moving with different velocities. Okay, why they are moving? Because here they are crowded, so they want some space. It's so simple, right? So now what we really need to do is we need to examine this overall mass velocity and average molar velocity and see that how can we quantify it. So now all of this is okay, but now how is the movement occurring? How we have to take, now there are different velocities. So if I am considering my observer here, I'm seeing this is moving to that, but if my observer is with the particle, what will happen? He will take that the particle is at rest, it will assume. So different places the observer could be. So for that, let's take the flux. Now we will take flux. What is flux? Any quantity divided by the area and time. So quantity upon time was okay, but now there is some area of diffusion, so we need to consider it. So we are considering that there's some area of diffusion, they like this part. Okay, so what next we have is that the observer, where is our observer? So observer is, if the observer is a stationary observer, okay, observer is stationary, okay, it will see that the particle will move with ui, okay, it will move with ui speed. And if we take the molar flux, then let's denote it as na, and sorry, ni, and so because this is molar, so this is ci into ui, okay, ci, this concentration is moving with ui. So because the particle, the observer is stationary, so this will appear. But what if the observer is moving with the particle, and the particle, we assume it's moving with an average molar velocity, the whole system is moving with average molar velocity. So in that case we take ji suppose, then it's ci, so it's moving with ui, it's saying that it's moving with ui. But if we take in respect with the molar average velocity, then we have to minus u. So this is the net velocity, like ui moving towards it, but because the observer is also moving with u, so this vector minus this vector is actually ui minus u vector, ui minus u vector, u, capital U. So Fix told us that okay, this is good, but what is the criteria of this diffusion, and what is the criteria in which we can put these all velocities? So there's a fixed law of molecular diffusion which says that this Ja is directly proportional to concentration gradient of the species A. So here, why this is occurring? Because the movement, that is the flux Ji, now there is a concentration difference, so this is the driving force. This higher concentration to lower concentration, there's a concentration gradient along this distance, there's a gradient, and this then makes the particle to move. Okay, so the particle now will move. So Ja, we can write is at taking off the proportionality sign, we can take it as minus dAb dCA by dx. So what is this dAb and why it is minus? So dAb is the diffusion coefficient, and because the diffusion is opposite to the concentration gradient, okay, because we need to make this concentration gradient positive, because concentration is decreasing, okay, so and mass transfer is a positive quantity here. Okay, so we have this. Now according to J, we have two definitions. Let's equate them. So this is Ca U minus Ua minus U. Again, we have the definition of U says that summation of Ci Ui by C. So we put here J is equal to minus DAB dCA by dx, that is equal to, let's take Ca Ua minus Ca into, what is U? U is nothing but Na plus Nb upon C. Why is it? Because Na, we have seen Ci Ui. So this is Ci Ui, we can write it as Ni. So here Na plus Nb by C. And if we equate it all out, so taking the Ca terms with them, and this could be written it, we could write it as Na. So Na is equal to Na plus Nb Ca upon C and minus DAB dCA upon dx. So here we have this equation, a very useful equation, and we will next look forward how this equation could be used for various countercurrent diffusion or equimolar, or when there is no flux of B, so only A is diffusing. We will take various cases. Hope you like the video. Please like, share and subscribe.